Well, just to remind you of what Antti explained about Wilson's idea of how to understand critical models. First of all, critical models are scale invariant. And so he had the idea of constructing a map in a space of models that maps a model at one scale to a model at a larger scale. And if you have a scale invariant model, then that would correspond to a fixed point of this RG map. This RG map has some, RG fixed point has some domain of attraction, and that domain of attraction defines a universality class. And the universal properties of the critical model can be understood by studying the RG map in the vicinity of a fixed point. So that's the basic idea. And what I'm going to be talking about for the next 3 hours is a kind of implementation of that. So the topic for this hour is progressive integration. Or multi-scale integration, but it's the idea that we want to integrate out a scale. So I want to explain the way that we approach that issue. So for simplicity, I want to set n equals 1 mainly. So n, remember, was the number of components of the field. And occasionally I'll write formulas that involve general values of n just so you see how they enter, the general n enters into the formula. But you should think about the case of n equals 1. So phi is a map from lambda, this torus, which has size L to the capital N for some fixed L. Capital N eventually will go to infinity, maps into R1 for the case of n equals 1. Now, let's suppose that I have a matrix C, which is lambda by lambda. It's a positive definite matrix. Then I can define the Gaussian measure with covariance C, which does the following. So it's if I integrate a function of the field with respect to this Gaussian measure, what I'm doing is I'm doing the integral over r to the lambda for n equals 1 of f of phi times e to the minus 1/2 phi c inverse phi product over x in lambda of d phi normalized. All right, so that's what I mean by a Gaussian expectation with covariance C, very familiar object. And the C that I want to focus on is minus Laplacian inverse, but it should be a mass because the Laplacian on the torus is not invertible. So I'm going to add a little mass term on there in order to make it invertible. So C will be minus the lattice Laplacian on the torus plus m squared inverse. Without the m squared, there'd be a zero mode, and it wouldn't be invertible, so I want to include that. And you could also replace this minus Laplacian by a fractional power. And essentially, there's a version of everything I'm going to say during this hour for that case as well. So let's define z0 of phi to be e to the minus v0 of lambda and phi. And what is v0? Well, sometimes I'll use different arguments for v0. I hope it'll be clear from the context, depending on whether I want to emphasize the lambda or the phi. It's a function of both. And it's defined to be the sum over x in lambda of 1/4 of g0 phi x to the 4th plus 1/2 of nu 0 phi x squared. So it's the thing that shows up in the phi to the 4th model. And the main problem that we're going to be concerned with is the following. It's to compute a certain Gaussian expectation, which I'm going to call Zn of phi. And it's the expectation with respect to this Gaussian measure of z0 at phi plus zeta. So here phi is an external field, and the zeta is the integration variable. So this expectation is acting on zeta. So it's like here I'm going to write f of phi plus zeta, and all the integrals will be with respect to zeta, not with respect to phi. So there'll be phi dependence left over. If you like, it's the convolution of the Gaussian expectation with z0 that I'm talking about here. And so this is the same as the expectation of e to the minus v naught lambda phi plus zeta, where again the expectation's acting on zeta and phi is fixed. We want to do this computation uniformly in the volume, so that is as n goes to infinity, right? This is the side of this torus, or the period of the torus is L to the n, and we want to let n be going to infinity, so we want to do this uniformly as n goes to infinity and as m squared goes to 0. So why is this the main problem? Here's a lemma that gives you an indication of why it would be very useful to know what this Zn function is. So if I write chi n now for the susceptibility in finite volume, I'm going to be focusing throughout the rest of these lectures on the computation of the susceptibility, not on the other things that I talked about, like the critical two-point function or the correlation length and so on. This is kind of an example of that's representative of these sorts of calculations. This finite volume susceptibility, evaluated at g naught and at nu naught plus m squared, is given by this formula: 1 over m squared plus 1 over m to the fourth times 1 over the volume times the second derivative of Zn at 0 in the directions 1 and 1 divided by Zn of 0. So here this 1 is just the function which takes the value 1 for all x. Okay, so this Zn is that same Zn up there, the expectation of Z0 with this external field.
Sorry, can you just remind me which order the arguments of Zn came?
Zn is a function of phi.
Yes.
So this is take the directional derivative with respect to phi in the directions 1 and 1 and evaluate at phi equals 0.
Oh, okay.
So I'm going to prove this lemma, so then you'll actually see what the right-hand side is if it's not clear. It's a very simple calculation, but the point of it is it's supposed to convince you that this Zn of phi is a very useful thing to know about, because if I understood it completely, then I would know what this finite volume susceptibility was. So proof of this, it's very easy. What is the left-hand side? By definition, it's just the sum over x in lambda of the integral phi 0 phi x e to the minus 1/4, I need a sum here, sum over x in lambda, 1/4 g0 phi x to the fourth plus 1/2 nu 0 phi x squared. That's the phi to the fourth part, except the nu has an extra part which goes into the covariance. So there's an extra part here which is e to the minus the sum over x of phi x minus Laplacian plus m squared phi x, and then product over x in lambda d phi x, and then you normalize this whole integral here like that. All right, so that's the left-hand side. The susceptibility is the sum of the correlations. So here's the phi 0 phi x to give the correlation, and then we want the phi to the fourth coming in. So there's here's the g naught phi to the fourth term. Nu naught plus m squared is the quadratic term, and this is what we want to compute. All right, so I want to do the usual thing. which is to introduce an external field and differentiate with respect to the external field in order to bring down the phi 0 and the phi x. But first let's write this in the form of the Gaussian integration. So this part of the integrand is showing up already here, and it also shows up down here. So I can normalize with respect to the integral of that part, top and bottom, and what I'll end up with is the Gaussian expectation of phi 0, phi x, z0 of phi divided by the Gaussian expectation of z0 of phi. Okay, so the Gaussian expectation is taking care of the Laplacian part of the story, and what we're left with is the z0 part, which is the g0 and the nu naught. So now I said we do the usual thing, which is to write this in terms of a derivative of an external field. First of all, the denominator is just Zn at 0. Right? Unfortunately, phi is playing a different role up there as it is here, but that's life. So this is the integration variable. So this is Zn of 0 in the denominator. And in the top, what I want to do is to write it as so I claim it's equal to 1 over lambda times the second derivative at 0 of the expectation of e to the s plus t phi 1 z0 of phi. Because what happens if you take that derivative is, well, you differentiate with respect to z, you bring down a phi paired with 1. That's just the sum over x of phi x. When you differentiate with respect to t, you bring down another one, sum over y of phi y. Then you put s and t equals 0. That kills the exponent. And you're left with the sum over x and the sum over y of phi x, phi y, which by translation invariance is going to be there was a sum over x missing there. There'll just be one sum times the volume, and the volume factor is taken care of here. Now this I want to regard as just phi being paired with some external field j. And there's a standard trick in dealing with these Gaussian integrals of completing the square to get rid of a linear term like that. And so if you complete the square, up in the exponent of the Gaussian integral, it's just a translation of the field, phi, then what you'll find, it's an easy exercise to find that what results is a term e to the 1/2 j cj times zn of cj. Okay, this is true not just for j equal to s plus t times 1, but for any field j it would be true. So the jcj is a term that arises, it's sort of the constant term that shows up when you do the completion of the square. All right, so that's an elementary exercise in order to do that. It's just a kind of an undergraduate calculus problem. And now what is cj? So j is this constant field. C is 1 over the Laplacian plus m squared. The Laplacian part is not going to do anything, so you're just left with the 1 over m squared. And so this Cj is 1 over m squared times s plus t times 1. And so this factor up here is going to be s plus t squared times 1 c1. And that will be m squared times the volume. So anyway, this is just an elementary calculation. It might be not so straightforward to follow every step as I do it, but it's just simple. And now you can take the derivative. And when you take the derivative, you're going to get two terms. You'll get, because there's not going to be any cross term, so you'll get a term from letting your derivatives act here on the exponential, or act here. And when you're done, you get the right-hand side. All right, so the two terms are going to be these two terms. And the first term, the 1 over m squared, comes from differentiating with respect to s and t here. And the other term gives you a directional derivative of this function Zn in the constant direction after you've factored out those numerical prefactors. Right, so it's an elementary fact that the susceptibility can be written in this form. And so that's my motivation for focusing on this Zn of phi. Now here's another lemma. This one's easier. That if I have two covariances, C1 and C2, and I want to calculate, so now I'm back to integrating with respect to zeta here. I want to calculate the Gaussian expectation when the covariance is C1 and C2, C1 plus C2, that this can be computed iteratively like this. So on the right-hand side, the expectation with respect to C1 integrates out zeta 1, treating zeta 2 as constant. And then once that integration is done, there's dependence on phi plus zeta 2, and the second expectation integrates out the zeta 2. This is like a decomposition of the Gaussian field phi into a sum, the Gaussian field zeta into a sum of two independent Gaussian fields, zeta 1 and zeta 2, with covariances C1 and C2. So I'm not going to prove this, but it's just a kind of a fancier version of a very elementary fact that we teach our students in beginning probability that if xi are normal random variables with mean 0 and different variances, and that they're independent, then the sum is normal with mean 0 and variance given by the sum of the two variances. So this lemma is just a version of this in the multivariable case. So the way that we want to make use of this last lemma to compute Zn is to take this Gaussian expectation EC that we're applying to the function Z0 and to write that covariance as a sum of many covariances, where each term in that sum of covariances represents the field on a certain scale. I'll make this more precise. And then the progressive integration corresponds to applying this lemma where instead of having a sum of two terms, you have a sum of many terms, and you integrate out progressively, term by term, first with respect to fluctuations on the first scale, then with respect to fluctuations on the second scale of the field. So this is a way of implementing this map that takes you from one scale to another. That requires a covariance decomposition. And this covariance decomposition really is doing the step that can be, we've seen in previous talks, was done either by block spin or by doing the dividing up of the covariance in momentum space like Antti did. This is a third version of that same idea. So there are different ways of approaching the problem, and we're going to approach it this way with a certain finite range decomposition. So we want to take C and write it as the sum j equals 1 up to n of C sub j. And then we'll apply that lemma with n terms instead of just two terms. Now the properties that that the terms in the decomposition will have are as follows. And by the way, it's not just immediate to write down a decomposition that has these properties. It's kind of a research problem in itself that many people have studied, some of them in the room, David and Pronob Mitter and Roland, Bauerschmidt and Guadagni and Simon, and so lots of people have written papers about this. I recommend our book that I mentioned if you would like to see a summary of that. So what are the properties? So the first one is that Cj plus 1. So I want to think about these as kernels. So xy, the Cj is an operator. It has a kernel, and this is the kernel at xy. It's bounded by L to the minus j times d minus 2. I don't quite close the parentheses yet. And it also gives a bound on gradients, spatial gradients. So if I differentiate the discrete gradient with respect to x or y a times, then I get a factor of L to the j for each one of those gradients. Okay, so if a was a second derivative, there would be a 2 here. And then there's another factor, which depends on the mass. So remember that this covariance c that we're starting with is minus Laplacian plus m squared inverse. So there's a mass term there. And that mass kind of shuts things down on these estimates, makes these c's very small once j gets large enough. So 1 plus m squared L to the 2j to a power s. And this s is any power that you want. The constant will depend on what you choose s to be, but if you want s to be 1,000, that's okay. So that holds for all x, y, and lambda. And the second property is the finite range property, that once x and y get a certain distance apart, then this covariance is just going to be 0. And that distance is L1 distance greater than or equal to 1/2 L to the j plus 1. I'm going to interpret these properties, so I'll be saying more about them. So those are the two main properties. There are other things that you can say. There's a continuum limit for these things after they've been rescaled and so on, but this is what I need. All right, so how do we interpret these? Well, to understand these properties, you want to have a picture in mind where the torus lambda has been partitioned into blocks. So maybe I draw the picture over here. So lambda is absolutely enormous. N is going to infinity. But then I want to divide it up into blocks. So the torus itself has side length L to the n. A block here has side L to the j. And I'll do this for j equals 0, corresponding to a block being a single point, up to j equals n when there's just one block, which is the entire torus. So another picture, a piece of this would look like this. That the 0 blocks are just these points, and then there's a 1 block, which is like that, and then 2 block is like that, and so on. So there's these nested blocks which are paving the torus, partitioning the torus. So we'll partition lambda n, which has side length L to the n, into j blocks. So bj, script bj is the set of all j blocks of side L to the j. And j is going to go from 0 up to n. So these are the scales. Now, let's think about one of those covariances on a block. So if we have zeta is a field that we want to integrate, it has covariance. So if it's a Gaussian field with covariance Cj plus 1, then the variance of that field is what, at a point x is what you get by putting y equals x here. And let's leave this aside for the moment and not take any gradients. That variance has size L to the minus j times d minus 2. So the standard deviation of the field would be the square root of that. So this has size, typical size, L to the minus j d minus 2 over 2. And that's true not just if we're considering the covariance Cj plus 1, but if we added into that all of the later covariances as well, because these covariances are getting small in a geometric way, and so a sum of them is going to be dominated by the first term. So this is true also if we're integrating overall k greater than or equal to j plus 1 of ck. If we had that covariance, it wouldn't make any difference, except maybe the constant here. So if we're looking at a field that has covariance Cj plus 1, its size at a point is given by that L to the minus j times d minus 2 over 2. And moreover, if we look at the gradient of that, the gradient goes down by a factor L to the minus j, and so the field is not going to vary very much over a block of side length L to the j, because the gradient is of size L to the minus j. You multiply that by the side of the block, you get order 1. So it has this size, and it's roughly constant on a block. Now, this additional factor, excuse me, doesn't do much until, you should think about m squared as being very small. It doesn't do much until L to the 2j gets bigger than 1 over m squared. And then this does something quite dramatic. It begins to decay exponentially beyond that scale, which is called the mass scale. So there's a special scale, the mass scale, where the covariance starts to feel the fact that there is a mass term there, beyond which you get very rapid decay. So Cj plus 1 has an additional factor, L to the minus 2 times j minus jm times s for j greater than or equal to jm, where L to the 2jm is m squared, m to the minus 2. Right? It's where that m squared L to the 2j starts to actually play a role. From that point of view, what's happening in this progressive integration when we're integrating out our fields scale by scale, one covariance at a time, nothing really happens once you've passed the mass scale, because the covariance is essentially 0 at that point. Now, the hierarchical model has been discussed in Anti's lectures, and just to make some contact with that here, the way that the hierarchical model is defined is very similar to this, except, okay, there's one more point I wanted to make. So before I come to the hierarchical model, what is the role of the finite range? The role of the finite range is that if I have a j block here and another j block over here somewhere, that the distance between these two blocks is more than a half of L to the j plus 1. Well, these are j plus 1 blocks now. The distance between these two is more than a half of L to the j plus 1. And these Gaussian fields are not correlated if x and y have that separation. And so they're independent. And so fields in blocks which don't touch are independent here. That's what the finite range does. So zeta x and zeta y are independent if x and y are in blocks that don't touch. Okay, so let me come back to the hierarchical model now. In the hierarchical model, this roughly constant is replaced by constant. Okay? In the hierarchical model, the field is just constant on a block. And this last feature, that fields are independent in blocks that don't touch, is strengthened in the hierarchical model to say that fields which are in distinct blocks are independent, even if they touch. So that's a simplification of the model to impose those conditions. Replace roughly constant on a block by constant. Replace independent on blocks that don't touch by independent on distinct blocks. And so that's the reason why the hierarchical model becomes easier. All right, so I want to think about having integrated out the first j covariances. I'm about to do the next one, j plus 1. I want to think at that point about these j blocks as being points. The field is roughly constant on them, and so it's essentially the same field at each point. I want to think about it that way, and so I want to think about those blocks as being points. And this leads me to look at how big monomials are on those blocks. This is why the notion of relevant, marginal, and irrelevant comes into the story in this language. So let's look at some monomials. So for phi with covariance Cj plus 1, or the sum of all of the subsequent covariances is just the same. And for a block B in Bj, okay, at the previous scale, where the field is roughly constant, let's look at a monomial. So the sum over x in the block of phi x to the p. So in this picture, I'm looking at a small block in here, summing the field, summing a power of the field over that little block. All right, so this is just a kind of a back of the envelope kind of calculation to see what is roughly the size of this. So first of all, we've said that phi, here I called it zeta, but phi has this size. So it's about L to the minus j times d minus 2 over 2, and that's raised to the pth power. And it's roughly constant over that small block, and so I get the value when I'm summing over the block just by multiplying by the number of points in the block, which is L to the dj. So let's take d equals 4. And then d minus 2 over 2 is 1. So this is just L to the 4 minus p times j. We've seen this in Anti's talk. And if we plug in some different values of p, like p equals 0, we get L to the 4j. P equals 2, it's L to the 2j. P equals 4, it's L to the 0j. And for larger values, it's L to the minus p minus 4 times j. I changed the sign in the exponent to emphasize what's positive there. So these two correspond to relevant monomials. These terms are growing with the scale. The p equals 0 term is not going to concern us very much here because we're interested in the susceptibility. So there's a ratio there, and the constants, they don't play much role. So it's p equals 2 that's very important. This one neither grows nor shrinks, so this is called marginal. And this, for p greater than 4, is exponentially decreasing in the scale and corresponds to irrelevant monomials. All right. Let's go back to our goal, which was to compute this Zn of phi. So this was the Gaussian expectation of Z0 of phi plus zeta. So Z0 of phi is just e to the minus v naught of lambda and phi. It has the phi to the fourth term in it and the phi squared term. All right, so the way we're going to compute it is using this lemma here. As I said, we're going to take the covariance, we divide it up into a big sum of n terms. We apply the version of the lemma that has n terms in the sum rather than 2. And so we can compute this as e to the c n, e c n minus 1, e c 2, e c 1 of z0 of phi plus zeta n plus zeta 2 plus zeta 1. And again, you know, these integrals, they just integrate out the fluctuation field that has their label on it. And you want to think about this as if zeta 1 has captured the fluctuations of the field on the order of a point, zeta 2 on the order of an L block, a 1 block, zeta 3 on the order of a 2 block, and so on. And so we're just gradually integrating out the fluctuations of the field until there's nothing left. Now, of course, excuse me. There's going to be infinitely many of these integrations in the end, and we want to study a typical one. So integration of one scale will be written as zj plus 1 of phi equals expectation of zj of phi plus zeta j plus 1, where this whole thing gets started with z0, like I said. So z0 is e to the minus v0 of lambda. And I want to rewrite this. I don't want to keep on writing these phi's all of the time. So notation that I'll use for this is I'll write it as zj plus 1 equals expectation cj plus 1 theta zj, where what this theta does, it's a map, and theta takes a field and it maps a function of the field to f of phi plus zeta. All right, so the way that you read this formula now to make it look like that one is I evaluate the left-hand side at phi. That phi acts, is an evaluation of this theta, and this theta sub phi of zj just becomes zj of phi plus zeta. The zeta gets integrated out. So that's a shorthand notation. Now there's like two perspectives. Sorry, my voice is weak here. There's two perspectives about this. Perspective one is that this Zj is a sequence. That we're going to start with Z0, compute Z1, compute Z2, compute Z3, and so on as a sequence. The problem with that perspective is that we don't know where to start it, because we're trying to study the critical point, and we don't have a description of the critical point at the moment. We don't have our hands on it. We can't set nu naught equal to nu c, for example, because we don't know what nu c is. Part of the problem is to compute this nu c. So that perspective is not a good one. We should not think about this as defining a sequence. We're going to enlarge the perspective instead. So perspective 2 is that this is just a map. This here is a map which takes whatever z you put in here for Zj, and it gives you a new z. So maybe I'll write that down. It's a bit subtle, but it's quite important. Okay, the problem is that we don't know what Z0 is. I mean, I wrote down a formula that Z0 involves this G naught and nu naught. It's just determined by those two parameters, but we want to choose nu naught critical, and we don't know how to do that at the moment. Part of our problem is to determine what the critical point is. So perspective 2 is a wider one, which is to view this E Cj plus 1 theta as a map that takes any reasonable z to a new z. Doesn't have to be the Zj that's produced by some sequence. And I'm going to make an abbreviation in the notation where I'll just write this as E plus theta, like adding one scale, going to the next scale. So this Z plus is E plus theta Z. Now, a global trajectory would be one where you start with a specific Z naught and you're actually able to take E1 theta Z naught to get Z1, then compute Z2 from that, and so on. And that global trajectory is only going to exist in practice if Z naught is chosen to be critical in the first place. And so this is a way of kind of characterizing what the critical point is going to be in this context. It's the value of nu naught that is going to permit this indefinite iteration of the map to produce a global trajectory. And this flexibility that we have by not insisting on having a sequence, but rather having a sequence of maps, is going to allow us to, figure out how that global trajectory, what are the conditions, how is it created. So global trajectory so that's the indefinite application of this map. Will be possible only if V naught is critical. That's how the critical point will be identified. All right. So what I want to discuss next is the perturbation theory. there's sort of two parts to the story. There's the perturbative calculations, which we've already seen a lot of in Anti's lectures. And then there's the control of the rest, the non-perturbative part of the story, which I won't get to until tomorrow at some point. So the first problem in perturbation theory was already solved by Anti. So we want to find a VPT, I'll call it VPT plus, which is a new version of V, which is the 1/4 g phi to the fourth plus 1/2 nu phi squared. It has a new g and a new nu. So such that if I take the expectation of e to the minus v of lambda, that, well, I'll write is equivalent to e to the minus vpt plus of lambda. And what this equivalent means is as formal power series with error of order v cubed. When we're starting off, our initial z naught has the form e to the minus v naught. So this is a way of trying to understand what z1 might look like. And this is a much studied problem in probability theory or in analysis to figure out how do you take the expectation of an exponential. Well, at the first order it's the exponential of the expectation, but then there are correction terms and so on, and we want the terms up to order v squared. So there's something called the cumulant expansion, which says that the expectation of e to the minus v, I leave out the lambda for the moment, is e to the minus the expectation of v plus 1/2 expectation of theta v truncated theta v, the covariance term. And then there are higher order terms up in the exponent. So this is VPT. It's just this. The problem is that it's not of the allowed form that we want. We want VPT to look like V. It should just have the same form of V except have its coupling constants renormalized. And the first term, the linear term, is fine in VPT. If you take this expectation when V has terms of that are phi to the fourth or phi squared, you'll get back terms of phi to the fourth, phi squared, and a constant term. We're going to allow constant terms, so that's okay. But here you have a bit of a problem, which is that in this truncated expectation, these are v of lambdas. And so there's a sum over x in lambda and a sum over y in lambda. X in lambda here, y in lambda there. You factor out the sums. You have a sum over x and y of the correlation of vx and vy. And that's not of the right local form. It's not a local polynomial. It's not a sum of the monomials of the type that we've been looking at so far. And so that's an issue. And this issue has been mentioned a few times already in this conference. In the hierarchical model, it doesn't arise. It's another reason to enjoy the hierarchical model, is that this variance term is actually local in the hierarchical model. And this VPT, as I've defined it, is just going to be of the form of V with some quadratic correction to the coupling constants, to the coefficients of the monomials. If you're in the Euclidean model like we are, then you have to deal with this issue. And I'm not going to deal with it. All right, so it's just not something that I want to spend time on. We've kind of got bigger fish to fry than that thing. But there's a way of dealing with it. So if with the finite range covariant decomposition, what happens here is that there are non-local terms that need to be localized. So you want to move the phi y over to the phi x, perhaps at the expense of some gradients or whatever, if you want to do a Taylor expansion to a certain order. There's an operation that will take care of that. Another issue that shows up in the finite range covariance decomposition that doesn't show up in the hierarchical model or in the block spin model or approach to this problem is that there's a phi to the sixth term that comes in here, which is very dangerous in the exponent because its sign is going to be out of control. So there's a way of, so in the hierarchical, in the Euclidean model, the way to deal with this is to replace e to the v by something else, which we call I of v, which has an e to the minus v in it. So there's an e to the minus v lambda. But then there's also another term which depends on v and on lambda as well, that goes downstairs. So this term has non-local bits in it and a phi to the sixth term as well. Basically, we're going to have to be doing very accurate computations to second order in the coupling constants, to second order in v. And so this w is second order but irrelevant. We nevertheless have to keep track of it because we want to have third order errors ultimately. And so it's not a big deal to do this, but it's some effort is required and some organization. So let me tell you what the result is after the smoke clears as far as how this v flows. So maybe I'll just say one more word, that this equation here gets replaced in the Euclidean setting by an equation that says that if you take the expectation of this I of v, like this, instead of e to the minus v, then you get an I plus, which has a similar form to this with v replaced by vpt, the same vpt that I'm going to write down, and the w gets adjusted to the next scale. So there's some story here that I'm not really want to focus on because it's a bit of a side issue as far as the main thing is concerned. So you can do this computation, and here's what results. So it gives that vpt of phi x is equal to 1/4 gpt of phi x to the fourth plus 1/2 of nu pt phi x squared plus upt, which is a constant. And these coefficients, gpt, etc., are explicit quadratic functions of the coupling constants that are in v. So I'll tell you what they are after some simplification. So there's some change of variables that I also don't want to get into that leads to a simpler set of equations than what you would get if you just naively did the computation there, and nevertheless contains all of the useful information. So the equations, I'll just write g plus instead of gpt because it's not really gpt. So g plus bar, the bar also indicates that we're not talking about the initial variables, is g bar minus beta g bar squared. And nu plus bar is equal to nu bar times 1 minus n plus 2 over n plus 8. So here I'm inserting the general n value of the coefficient that pops out because it's actually an important term. N plus 2 over n plus 8 showed up in the exponents, the critical exponents, plus eta prime g bar minus c prime g bar squared. So these computations are really not mysterious. They're very mechanical. In fact, Roland Bauerschmidt wrote a Python program that does the computation and gives the answer in LaTeX code that you can just paste directly into your document, which is rather nice. For example, where does this beta come from? So that beta comes from, in this formula here, the g phi to the fourth, g phi to the fourth term. And if you want to pair g phi to the fourth with another g phi to the fourth to get a phi to the fourth, which you should because this is a coefficient of phi to the fourth here, it's this diagram here that we've seen before. So this beta is coming out of this bubble here. The reason there's a beta here as well is that this comes, so this is like a G and a G. This comes from a nu and a G. So nu has two lines coming out of it, phi squared, G has 4, and so it looks like that. And so again, you see this bubble coming in, but the combinatorial factor is a little bit different. Depends on the number of components. And you know, this is really...
Don't you have an L there in the second line?
No, I don't have an L because I haven't rescaled anything yet. So I will want an L. I'll want an L squared, actually.
Okay.
But at the moment, there's no rescaling. So this is also a difference between what we're doing here and what Antti was doing, and I think maybe what most people do, is to rescale the lattice as you go along. We've never changed the size of the lattice spacing. So the lattice spacing always just remains 1. And the rescaling is done in a different way. So the scaling is in the covariance. It's gone now, but you see it in the monomials, that the monomials are scaling because the covariance is scaling down. So I am going to want to do what you said and change this variable to another variable so that the L squared will appear. Right. But at the moment, for nu, it doesn't show up.
G bar and nu bar are what?
They're sort of avatars for G and nu. So this simplification that I mentioned over here is that there's a slight change of variables that simplifies the equation so that they have this form. And so the bar is just reminding me that I made that change of variables.
But what is it? Is it a linear combination or?
No, it's nonlinear.
But it's some simple.
It's explicit. It's explicit. Yeah, it's an explicit nonlinear transformation that simplifies the form of the equations. So if you just did what I said there, you would have a G nu term up here.
But here is this n plus 2 divided by n plus 8 first appearing. So will we understand why it is appearing there? Or
I'm not going to derive that formula for you, but I think maybe you can imagine that when you plug in here, so what does the theta do? It replaces the integration variable by integration variable plus phi. So you have here phi plus zeta to the fourth and phi plus zeta to the fourth. And so if phi is a multi-component field, you know that fourth power is the square of the Euclidean norm of it's the square of the Euclidean norm of the field. And so there are components all over the place. And a phi I here is going to be looking for a phi I to pair with over there, not a phi j. And this n plus 2 and n plus 8 are just counting how that happens. So they're just purely combinatorial numbers that show up by the computation of this variance term.
So if the lattice size was 1, it would appear on those 8' I' terms.
Yeah, so I am going to tell you exactly what the beta is, and I'll tell you what the eta prime is. I won't tell you what that is. I'll leave that one to your imagination. But they're strictly functions of the covariance. That's all they can be, right? Because we're doing here a Gaussian expectation with respect to a certain covariance of some explicit function, and we're calculating the coefficients of the polynomial that arises, and the only thing that they can depend on is this c. So, well, I'm sort of out of time here, but maybe just so that you're not in too much suspense. So, e.g., what is this beta? it depends on j, depends on the scale because the covariance does, and it's n plus 8, the combinatorial factor, times the sum over x in the lattice of wj plus 1 squared. This is a different w than that one. This is a little w. Where w is the sum of the covariances up to this point. So it's a calculation. I'm not planning on doing it, but this is what results. Now the behavior of this beta is very important, how it behaves as j goes to infinity. In dimension 4, it converges to a constant. This is, as j goes to infinity, this is becoming the L2 norm of the covariance, which in the massless case would be divergent. And so this is a difference between two quantities which want to diverge, and that difference turns out to be bounded. Anyway, so we'll come back to this tomorrow. I think I better stop now. I'm out of time.
Thank you very much. Further questions?
Yes?
I want to just to be sure. So the exponents of the log in the theorem you wrote before this one are just the factor there, and the log is due to the fact that the sum of the g gives a log. So should
yeah, exactly. So I will show you. I will show you that in detail. I'll solve this equation. I'll solve this equation. I'll show that this n plus 2 over n plus 8 gives you the power of the logarithm. I'll do that tomorrow.
It's connected to that n minus 2 and minus 8 there, right?
This n plus
I mean,
this.
yes.
Yeah, it's just this, right? Yeah. It's,
I don't remember that.
Further questions?
David.
Did you want to mention the gradient, Laplacian term in there? Because this is a hierarchical formula. That doesn't have to be.
So David has noticed that I did not mention the wave function renormalization, which is necessary in the Euclidean case, but not in the hierarchical case. So in the Euclidean case, if you did this computation, you would find that you should include another term, which is 1/2 some other so yeah, you should include that term. So in the hierarchical case, that term is irrelevant. In the Euclidean case, it's marginal. It creates headaches, actually, because of that. But yeah, I have to leave a certain number of details out, otherwise we don't get to our goal. Yes?
So, for example, to study this 4 minus epsilon dimension, instead of using long-range model, if you just look at the torus, but with one special direction to be shorter, like, L by L by L to the 1 minus epsilon power, would everything work?
I don't think so. In fact,
What's the question?
So if you treat 4 minus epsilon dimension by L by L by L by L 1 minus epsilon.
I think that'll give you a three-dimensional.
Trivial wave function renormalization. Constant.
No, I don't think the question was about wave function renormalization. I think you're asking about whether a different way of thinking about the epsilon expansion. Am I right that the theorem 2 from this morning was a theorem about epsilon expansion, which was realized in terms of a long-range model?
Right.
I understood you to be proposing a different way of realizing a model which corresponded to dimension d minus epsilon,
Right.
and I don't think it does.
So it has to be isotropic.
also.
This is anisotropic. This is a slab.
Yeah, so but I think that dimension is just going to, it's just going to disappear.
A study sort of approach to.
Either it is 3-dimensional or it is 2-dimensional. It depends how thick it is.
Well, he had 3 dimensions of L and 1 dimension.
Yeah.
Yeah.
But you know, the
Anyway, I think
height of the slab determines whether it's more like 2-dimensional or more.
I think you lose the short dimension. I didn't say that in the long-range setting, the only thing that changes in this picture is the covariance decomposition. So the covariance is different, but the covariance is actually an integral. The long-range covariance can be written as an integral against a certain kernel of the short-range covariance, as I learned from Pranav Mitter in one of his papers, which was very important for me. Then the rest of the story goes the same way, except this d minus 2 becomes d minus alpha. And this 2 becomes an alpha, and this 0 becomes an epsilon. And so this marginal direction becomes relevant in that case.
Good. Maybe we go for lunch.
Okay.
So this just to understand better. So this transformation is just to eliminate the integer or for